OK, so we're not really done talking about subtleties here. And we're not really done talking about sort of some of the key ideas that come into these calculations. I've given you a very simple example of just the coupling, but it's a little bit too simple. So I want to do something a little more sophisticated, but still fairly simple and widely used. And that is in the standard model just to take the heaviest particles, which are the top, the Higgs, the W, and the Z, and remove them. So we'll spend a bit of time talking about what happens when you do that. That's not the only thing you could do. And in particular, before people knew how heavy the Higgs was, you could think of other possibilities. And before people knew how heavy the top was, people did think of other possibilities. This is actually a reasonable thing to do, though. So let me give you one example of another possibility. Well, you could say the top is heavier than the W and the Z, so why don't I do the top first? And then I'll just follow your diagram over there. Or we erased it, but it'll follow the picture. And then I'll do some running in the theory without the top quark, and then I'll get down to the W and the Z scales. Then I'll remove the W and the Z. OK, that would be a valid thing to do. But it introduces complications that are actually not worth the effort. And the benefit is actually not that great, so I want to emphasize that. When should you think of things as being comparably heavy versus when should you think of things being hierarchically heavy? Well, one complication of removing the top quark is that it breaks SU2 cross U1 gauge invariance, because the top quark was in a doublet with the B, and you're trying to keep the B and remove the top, which doesn't sound good. You're trying to keep the gauge particles, the W and the Z, in your theory, so you should still have that gauge symmetry, even if it's spontaneously broken. But you're trying to remove one member of a doublet. And that leads to Wess-Zumino terms that you'd have to include in the effective theory, so you can deal with it. And it's just a little bit annoying. But, it's something you can deal with. The real crux of the matter is that if you compare mz over m top, or mw over m top, that's about a half. So if you think about what you're expanding in when you take external particles that have momentum of order mz, integrate out particles of order mt, you're expanding in a half, which is not such a great expansion parameter. Usually in effective field theory, we want to expand in something that's at least a third, hopefully a quarter. And a tenth if you really want to have a good expansion. So a half is not really that good. So that's the real reason not to do it. And you could ask, well, what do we lose by not doing that? And that, of course, is the real question. Well, you miss some running, right? Because you don't have a theory that has no top quark but still has the W and the Z, and that theory could have anomalous dimensions, and you'd miss any running in that theory. You're kind of collapsing two of the lines in my picture with the arrow between. You're collapsing them down to just a single line. So you're missing the running that would go between MT to MW. Well, of course, that's not a very big hierarchy in its logs of 2, and that's why we don't care that much. What it boils down to is that you're treating alpha S of MW, and if we want to be generous, we can say it's MW squared over M top squared, so they're logs of 4, that you're treating this perturbatively. If you remove both the top and the W at the same time, then this is going to show up in your matching conditions, and you're not thinking of that as something that's large. You're thinking of it just as order 1. OK, so that's the cost, which is not a big cost. especially when you say that the cost of going the other way would be expanding in a half. Better to take the cost in the logarithms than in the expansion in the half. Okay, so that's a general kind of rule that if you're thinking about removing massive particles, you should ask how close are they to each other? Should I integrate out a slew of them at the same time or one at a time? And that'll depend on exactly the scales in the problem. And it means you're organizing the theory differently if you do the two different approaches. All right, so we'll do an example of this. We'll take a very simple example, although not completely trivial. So just B quarks changing to charm quarks, U bar and D. So in the standard model, which is where we start, let's say, we have a W boson, we have an up quark that's left-handed, we have a CKM matrix connecting flavors together, and we have down quarks. So there's a matrix space here in the flavor, which includes bottom charm, up and down. And tree-level matching is easy, and some of the complications I want to talk about will come into the loops. So let's first get through the tree level and set up some notation, and then we'll talk about what happens with the loops. So tree level, this is the diagram in the theory 1. Just calculate it at tree level. W propagator, unitary gauge. And then there's some spinners. So we have an anti-quark, so we have a V spinner for the anti-quark. It's an up. Everything else is a U spinner. I've put in explicitly the P lefts to denote the fact that it's left-handed. So there's some momentum in this diagram, which is the momentum transfer, which is the B momentum minus the C momentum in a kind of obvious notation. And of course, by momentum conservation, that's also the D momentum plus the U momentum. And that's the momentum that's going through the propagator. We're going to count momenta as being of order masses. And the heaviest mass in this case is the B quark mass, so we'll take it to the B quark mass. We can use the equations of motion. So PB slash on UB, spinner for the B quark, is MB UB, etc. And we can simplify the diagram by doing that. And of course, the key thing is that we can expand the propagator since the momentum is smaller than the mass of the W if we're integrating out the W. So the leading term when we do that is this term. And any other terms that we drop are down by that much. So for example, this term here, we've just said that the k's are of order mb, so it's down. And then we could drop the k squared here relative to mw squared, so we just have that. And then we put that together, we can calculate the Feynman rule and the effective theory. The Feynman rule and the effective theory, we can determine the coefficient of it. So let's start out with just saying it's some four-quark operator that couples together those flavors, conveniently chosen so that they're all different to avoid combinatoric factors. And in some conventional normalization for this Wilson coefficient, we call it GF, which is for Fermi. And And the Feynman rule would again give spinors, and the same spinors as before. We have the same Lagrangians for these light quarks. Haven't changed anything about that. We're just removing the heavy particle. And it's conventional also to pull out the CKM factors so that. OK, so if you like, you could say that there's a coefficient here, and that coefficient's been fixed to be 1. And what this G Fermi is then would just be the leftover factors of the gauge coupling and the mass of the W. And that's the usual convention. OK, so G Fermi is just fixed in this case, not as the thing that is going to get corrected at higher orders in QCD, but would get corrected at higher orders in electroweak if you like. And then you sort of put in the QCD corrections into some other coefficient that we can call C, and we'll just say that it's 1 at the level of this. Then this line agrees with the expansion of that line, and that's the matching of something that's measurable, which is this 4-point function. So we can call it an S matrix element. So this theory is very popular. It's called the electroweak Hamiltonian. It's used all over the place. And it involves more than just doing what I did because I chose a particular set of flavors for a particular channel, and you have to do it for the whole, for all sorts of other channels as well. So we'll study some aspects of this theory. We won't study every possible aspect. I've given you a handout that studies a lot more. It's 250 pages long. I'm not asking you to even read all of that. I've pointed you at some pages of that in the reading, which are relevant to the discussion we're having here. If you really want to dig deeper, you can. So people often call this an electroweak Hamiltonian, which is just minus the Lagrangian. So then that's 4GF over root 2. And as a Hamiltonian, we write fields instead of spinors. So we have this 4-quark operator. And we would have determined the Hamiltonian from tree-level matching from what we've done. And this would be the result. OK. Standard stuff. How do we want to go further than that? Well, if we want to think about theory 2, which is this theory, and we want to think about it in more detail, we should worry about whether we're, with just this operator, whether we've got a complete set of structures that could possibly occur. So we should think about the symmetries. And it's useful to, therefore, construct the most general basis of operators in theory 2. And we'll just do that. So if you read this 250-page review, then it's done for the full electroweak Hamiltonian. And we'll just stick with the flavors we're talking about here. So what are the most general bases of operators? How should we think about that? Well, we're constructing some theory that we're matching onto at mu equals mw. And at that scale, when we're determining the theory and determining the coefficients of the theory, we can treat the bottom, the charm, the down, and the up effectively as if they're massless. And really what I mean by that is that the masses of these particles are only going to show up in the operators and not in the coefficients, which I've the C that I talked about over here. Okay, the thing that shows up in the coefficients are the mass scales we're removing, and we're not removing the mass scales of these things. So that means if we can think of them as massless, that we can think about the matching in terms of using something like chirality. And we can use the fact that QCD for massless quarks does not change chirality. And we can use that in constructing our basis. So that means even though the B quark and the charm quark really have masses, for the purpose of constructing the operator basis, we can think of them as massless, and we only have left-handed guys to worry about here. Chirality means more than that. It also, well, it means effectively that, but it means also that we will only get one gamma matrix here. And we can think about why that is. Chirality means that you'd get an odd number. You need an odd number to have left on both sides. But you can reduce 3 to 1. So there's an identity, which I won't write out for you, but you can reduce 3 back down to 1. So any higher odd number can be reduced back down to 1. So once we use chirality and that fact, then we have a fairly restricted basis. In terms of Dirac structures. You could ask, what are the most general possible ways of contracting spinor indices? Who said I had to put this charm quark with the bottom quark? I could have put the up quark over here. And maybe at high orders that happens. Well, at high orders you could think about that happening, but you can always get back to the form that I wrote over there using this, what's called the spin fiords. So if I write it for fields, it means that there's an identity that I can rearrange this guy the other way, and so these are equivalent operators. And sometimes you have to use these relations when you're doing matching calculations, because you've constructed a complete basis, which is the minimal one, and then maybe when you're doing a calculation, you get this operator, so you have to turn it back into this one. There's 2 minus signs in this relation. One is from the Fierz identity, and one is because when you do the manipulations, you end up anti-commuting 2 fields. So from the statistics. So if you were to use the same relation for spinors, then there would be 1 less minus sign, something to be careful about. So what this tells you, once you put that information together, is that you know that you can write the operators this way, and you also know that this gamma, capital Gamma, has that gamma UP left form in terms of the Dirac structure. So the only really thing that can happen is color. And you can contract the color of these 3s. So you have 4 3s. You can contract the color of them in different ways. Well, you have 2 3 bars and 2 3s. Think about having different color contractions. And that will expand our operator basis by 1 more operator. There's also a color Fierz. And I can use that color Fierz to get rid of having explicit TAs. So color is a lot like spin in the sense that if I had more TAs, I can always reduce a higher number of TAs back down to a lower number. So if I had 2, I can reduce it down to 1 or 0. Okay, so I only really have to think about having a TA here and a TA there. If I have a TA there and a TA there, there's a color Fierz relation for this guy, which you can use. And there's a handout that I posted on the web that has a summary of all these relations. I'm not going to bother writing them down in lecture here. So once I take that into account, then there ends up being 2 operators. And if I were to write them in a kind of renormalized notation, where I introduce the scale mu, then I would write them as follows. Let's call them O1 and O2. And the difference between O1 and O2 is just simply a color. So in O1, the color index alpha is contracted between charm and bottom and down and up. And then in O2, it's the the color is contracted the other way. So I don't write explicit TAs, but I do have to consider the other possible way of contracting the indices. Up, down, doesn't matter. OK, so these operators, these are the two operators they have once I satisfy all the symmetries, and I have some coefficients. And if you ask really what the coefficients can depend on here, well, they can depend on mass scales like top and the other particles that I'm integrating out, z. I'm not going to make that explicit in my notation. If I tried to make every possible mass scale like the Higgs over the top, it would just be too much. So let me just denote two things that it can depend on. Mu over mw can show up, and alpha of mu can show up, as well as some ratios of other particles, which we will suppress. So then what tree-level matching is saying is that you got one of these operators and you didn't get the other one. So it says that at tree level, what we did before, let's just say we do matching at mu equals mw, and C1 at 1, which is mu over mw equals 1, and alpha at mw is 1. And then corrections to that would be suppressed, no large logs, just by alpha. And C2 of 1 alpha of mw is 0 plus something of this order. So that's what we've determined by doing our tree-level matching. Now, when we did our tree-level matching, we did something. We used external states which were quarks. We matched up the S matrix elements in that way. If you were really interested in this process, B goes to C, U bar D, you'd not really be interested in measuring quarks. We don't see them. You'd be interested in thinking about the process for mesons. B meson changes to a D meson, and a pion, for example. And who's to say that the matching that we did for quarks is also the matching that's valid for hadrons? Well, it is. So there's a key fact about matching, which is important. One of the things I wanted to emphasize to you is that it doesn't depend on what states you pick. It's independent of the choice of states, and it's independent of the IR regulators that you pick. So when you do matching, you often pick some IR regulators to regulate IR divergences. And the only thing you have to do is pick the same states and same IR regulators in the two theories. And once you do that, your results for your coefficients will be independent of the choice you made. So this is intuitively something I think that's, once you think about it, fairly obvious. What this sentence is saying is that the matching, which is supposed to be a high-energy property, is independent of the low-energy physics. The choice of the states and the choice of IR regulators, that's parameterizing something about low-energy physics. Lower energy than the scale we're trying to determine. These things should only depend on high-energy physics, so the outcome for them will be independent of this choice. So just to emphasize, even when we use hadronic states, the result that we obtain from quark states is valid. That's just different choice of state. And what we're doing when we do the matching is we're picking a convenient choice of state. Something that makes it easy to calculate. If we tried to calculate the matrix elements with B and D and pi mesons, then I'm saying if you're strong enough, you'd get the same matching coefficient. Of course, you should pick the result that makes the calculation easy, and that would be to use quarks. Any questions about that? Okay, so this is something that you should keep in mind. And you should keep in mind that you do have to make sure that you're using the same states in IR regulator in the two theories. In this case, that's pretty easy. The states are really the same states because you're defining the states with the Lagrangian for the B quark, say, and the B quark Lagrangian hasn't really changed. So there's no change to the state. And you can set things up so that you have the same IR regulator